Hey everyone, let's dive right into this explainer and uncover exactly how we measure temperature, along with the totally clever science hiding inside our everyday thermometers. We interact with temperature every single day, right? From checking the weather app to cooking dinner. But the actual mechanics of how we measure it are deeply fascinating. It's not just about reading numbers on a digital screen, it's a story about physics, physical properties, and building a standardized language of science. Today, we're taking a pretty fascinating journey. We'll kick things off by figuring out if our own senses are actually reliable. Then we'll dive into the scientific principles behind temperature, check out how different thermometers use physical changes, and wrap up by learning how to calibrate the Celsius scale totally from scratch. All right, part one. Are our senses actually reliable? To get started, I want you to picture a scene that plays out in living rooms literally all the time. A mom and dad are arguing over whether their baby has a fever, and their only medical tool? The palms of their hands. It's a classic, right? Well, this brilliant everyday example highlights a massive scientific flaw. Two people can feel the exact same object and come to completely opposite conclusions about how hot it is. Why? Because the mom's hand might have been freezing cold just a minute ago, so the baby's forehead feels super warm to her. But the dad? Maybe he was just holding a hot cup of coffee, so to him, the baby feels completely cool. Their internal baselines are just totally different. And if you want proof that we really can't trust ourselves, just try this classic junior science experiment. You put one finger in hot water, another in ice water, and then plunge both into a single bowl of room temperature tap water. Your own two fingers will literally disagree with each other. The finger that was in the hot water is going to scream cold, and the ice water finger is going to yell hot. It's the exact same water, which absolutely proves our built-in human sensors are totally useless for making an objective comparison. Moving on to part two, the scientific principles of temperature. Since our hands are terrible at this, we have to rely on measuring temperature. Scientifically speaking, temperature is the precise, objective measure of an object's degree of hotness. It's really important to separate this from how hot something feels to us. That's heat transfer. Temperature is about the actual state of the object itself. So whether we're talking about the blistering surface of the sun at 5,500 degrees or freezing liquid helium down at negative 269 degrees, temperature gives us a solid universal number we can actually trust. That brings us to part three, thermometers and physical properties. Here's the catch. We can't just look at an object and magically know its temperature. We need a proxy, and that's where thermometers come in. All thermometers work by piggybacking on something called temperature-dependent properties. That's just a scientific way of saying they use physical traits of a substance that predictably change when things get hotter or colder. By measuring that physical change, we're indirectly figuring out the change in the temperature itself. Pretty clever, right? There are actually a bunch of ways to do this. A classic liquid and glass thermometer, it measures the expanding volume of a liquid. Those infrared thermometers we use for quick body scans, they're measuring the intensity of invisible infrared radiation coming off a hot object. And then you have those highly precise resistance thermometers, which literally measure the changing electrical resistance in metals as they heat up. The whole game is just finding a physical property that reliably scales up and down with hotness. Now, if we want our liquid and glass thermometer to be super sensitive, meaning it shows a really obvious visual change for just a tiny little shift in temperature, we can actually tweak its design. We could use a larger bulb so there's simply more liquid in there to expand, or we could use a much narrower glass tube, which forces even a microscopic increase in volume to travel way further up the glass. It's basically a mechanical trick to magnify that physical property. Even the liquid we choose to put inside makes a huge difference. Alcohol and mercury are the big ones, but they have major trade-offs. Alcohol is non-poisonous and super safe, which is why you see it in schools, and it's great for really cold temperatures. But it's a poor heat conductor, so it responds kind of slowly. Mercury, on the other hand, gives you a super fast response and is amazing for high temperatures. The catch? It's highly poisonous. So, we have to handle those with serious care. All right, our final section, calibrating the Celsius scale. So, we've built our tool, but how do we turn a completely blank glass stick into a useful scientific scale? Well, just like a ruler needs its markings, a thermometer needs anchors. We call these fixed points, two very specific temperatures in nature that are incredibly stable and easy for literally anyone, anywhere, to reproduce in their own lab. Our lower fixed point is the ice point, officially defined right at 0 degrees Celsius. But pay attention to the strict rules here. It has to be pure melting ice, and it has to be at normal atmospheric pressure. If you toss some salt in the water, or if you try doing this on top of Mount Everest where the atmospheric pressure is lower, that melting point shifts. Those strict conditions are absolutely crucial for consistency. Then we have our upper fixed point, which is the steam point, locked in exactly at 100 degrees Celsius. And again, the rules apply. This is measured using the steam right over pure boiling water at normal atmospheric pressure. By using these two perfectly reliable states of water, we get our universal anchors. With those anchors, you can literally build a thermometer from scratch in 3 incredibly logical steps. First, put your unmarked glass tube in the ice, let the liquid settle, and scratch a mark. Second, put it in the boiling water, let the liquid rise up, and scratch another mark. Finally, take a ruler and chop the space between those 2 marks into exactly 100 equal divisions. It originally used to be called centigrade, meaning 100 steps, but today we honor the Swedish scientist Anders Celsius by calling it the Celsius scale. Now, here is the really fascinating part. When we draw those 100 little lines, we're relying on one huge assumption that the liquid expands perfectly evenly or linearly between 0 and 100. We just assume that halfway up the tube, the liquid has expanded exactly 50%, so that must be exactly 50 degrees Celsius. We're essentially drawing a perfectly straight line on a graph from our lower point to our upper point. But I want to leave you with this somewhat provocative thought. What if nature doesn't actually draw a straight line? Because honestly, some physical properties don't change perfectly evenly. So if our whole scale assumes a perfectly straight line, but the physical property actually curves, how do we possibly know what the true 50 degrees really is? It's kind of a wild puzzle, and it's exactly what pushes scientists to constantly refine how we measure the world around us. Thanks so much for exploring the science of temperature with me today.